Welcome back. I'm Nan Jokerst, and this is an in-depth video about vacuum deposition of thin films. We use vacuum systems to deposit thin layers of materials, such as metals and insulators, onto our substrates. The thicknesses of these vacuum deposited layers are very thin, on the order of 5 nanometers to 250 nanometers. The three most common thin film vacuum deposition techniques are thermal evaporation, electron beam evaporation, and sputtering. In this video, I will introduce you to the process of thermal evaporation. Vacuum systems are used to deposit thin layers of ultra-high purity materials onto our samples and substrates because air molecules that are present during deposition will become impurities in our deposited films. So we remove the air from the chamber in which we are doing the film deposition using vacuum pumps. So vacuum deposition is any process in which a thin layer of material is deposited onto a surface in a high vacuum environment. As shown in this animation, the atoms come from an ultra-high purity material that we call the source, and atoms from this source travel through the vacuum in the vacuum chamber and are deposited onto the surface of our substrate. This process is called physical vapor deposition, or PVD, and requires vacuum environments with pressures on the order of 10 to the minus 6 torr, or equivalently 1.3 times 10 to the minus 4 pascals. We also require high purity source materials, typically 99.999% pure, 5 nines, or even better. These high purity materials include metals such as gold or aluminum, or an insulator or dielectric such as silicon dioxide or silicon nitride. These are available by purchase from many sources. The first of the three PVD techniques is known as thermal evaporation. Thermal evaporation uses heat to evaporate the ultra-high purity source so that it goes from solid to liquid to gas. The gas atoms travel through the vacuum in the vacuum chamber, and when these atoms hit the substrate, they condense and form a thin film on the surface of the substrate. We can use an everyday example to understand thermal evaporation. In this example, heat is used to melt ice into water, and the water is heated to the point of evaporation. The water vapor, which is now in the gas state, travels to the surface of the lid, at which point the vapor contacts the cooler surface and condenses. Metals and dielectrics can both be deposited using this vacuum thermal evaporation technique. But thermal evaporation is typically used most for metals, since metals melt at pretty low temperatures and produce very steady deposition rates. To conduct a thermal evaporation, a small amount of our source material is placed into a container called a boat. The boat is heated by passing a large electrical current through it to heat it up in a process called resistive heating. The boats that we use are typically tungsten. Why tungsten? If we want to melt a metal, its container, the boat, must remain intact during heating. That is, it shouldn't melt along with the source. And we need to conduct a large amount of current through this boat as well. So we use tungsten boats because tungsten has a higher melting point than our source metals, and it's very electrically conductive, allowing resistive heating to occur. Let's look at the mechanics of thermal deposition. The tungsten boat is clamped between two electrodes. An electric current as high as several hundred amps passes through that tungsten boat, which undergoes resistive heating. Just like an incandescent light bulb filament, it heats up and glows. As the boat heats up, the metal source material in the boat melts and then evaporates. These evaporated metal atoms travel through the vacuum chamber, strike the surface of the substrate, and condense, forming our thin layer of the source material on our substrate. Here's another good question. When should we stop depositing our source material onto the substrate? Well, we typically have a target thin film thickness for each of our processes that we conduct. So that means that we want to monitor the thickness of our deposited film on that substrate in real time during the deposition. So to monitor this film thickness, we place a crystal sensor in the vacuum chamber so that the source material is deposited onto the sensor at the same rate as onto our substrate. This crystal sensor vibrates, and the vibration frequency changes as the film is deposited onto the crystal, enabling us to sense this change in vibration and calculate that deposited film thickness as the deposition is taking place in real time. When the desired thickness is reached, we stop the flow of electrical current through the boat, which stops the heating of the source and halts the deposition. Thermal evaporation is one thin film vacuum deposition option. Be sure to look at the electron beam evaporation and sputter deposition videos to learn about two other commonly used thin film vacuum deposition techniques.